Thank you so much for having me and the opportunity to present our efforts on this project. My name is Shixiang Zhu, or simply goes by Woody. I'm happy to representing our team from Georgia Tech, including Professor Wong, Professor Xie, and the collaborators from Atlanta Police Department. In this presentation, I will tell us a bit about the existence of geographical disparity in access to the police resources around the city of Atlanta and why it's been so difficult to address the problem. And then I will talk about data-driven optimization framework that we developed and the details of the police operations simulation model that help us prove that redistricting would both improve the police operation efficiency and make Atlanta a safer place. Lastly, I will talk about the remarkable successes that we had in terms of the implementation of the proposed districting plan in practice. First, I want to start by telling you about a true story that I learned 2 years ago. A friend of mine who is a young lady living in Buckhead, Atlanta, one day she called the police and reported that a thief slid into a car and stole her valuable items while she was pumping gas near her home. Such type of crime, which are usually called slider crime, are unfortunately on the rise in our city and throughout the region. Slider crime can happen in the blink of an eye. However, in this story, it took the police more than 10 minutes to arrive at the scene, and the thief just vanished in the crowd. As a consequence, this crime drive a lot of residents to move away from Buckhead. Some of them, like the lady I just mentioned, decided to move to Sandy Spring, about 5 miles north of Buckhead, where average response time of police is significantly lower. So what we have learned from this story is response time is of the essence for both police and the victims when it comes to stopping the crime. So in the rest of this talk, I will give you some insights behind such phenomenon of rising crime rates and continually increasing police response time in Atlanta. Specifically, this presentation can be divided into 3 parts. As the first step, I will give you a little background about Atlanta and its police force. You probably know Atlanta, as the capital of Georgia, is one of the most populous cities in the states with more than 5 million people living and working here. And as the major law enforcement agency, Atlanta Police Department maintains more than 2,000 police officers that perform a myriad of services and have been dealing with more than 3,000 cases each day. Just like the example we mentioned early on, it has long been a serious problem that certain neighborhoods of Atlanta are suffering from increasing crime rates. According to the report from a major local newspaper, AJC, residents have been reporting car thefts, burglaries, and armed robberies in the traditionally low crime areas such as Buckhead. At the same time, response time in Atlanta rises sharply in recent years and exceeded the national average in 2018. Buckhead even reaches 30 minutes at a historically high level. Additionally, the police officers in this area are also overwhelmed by the long shifts and excessive working hours, which may lead to a host of public safety issues and create extra financial pressure for the police department. This phenomenon is closely connected to the disparity of the police workload throughout the city. So let's look at this map. Due to the population growth throughout the last 5 years, the overall police workload has been increasing rapidly. The color indicates the average police workload level from 2013 to 2019, in which 2018 and 2019 are the predictions. As you can see, there has been growing imbalance of the police workload among different regions. So Atlanta Police, which was under enormous pressure from local residents, has a very strong desire to reconfigure their zone plan, which had not been changed for over a decade. Their goal is to rebalance the police workload, shorten the response time, and eventually set back the surge of the crime. So one day, the APD reached out to us. They were hoping that we can give them more insights about the zone plan by taking advantage of the power of big data. We actually had our first collaboration way back to the end of 2016 because of another project. The first collaboration was fantastic. The project develops an algorithm that helps police identify the underlying crime linkages where the algorithm has been adopted by the police and deployed in the well system. So in summer 2019, they offered us this opportunity once again. And eventually we worked with the police and successfully implemented the new design in March 2019. Here, the words quoted from APD Deputy Chief Jeff Glazier will explain the goal of this project. He says that it is important that we examine our officer workload periodically. And with the help of Georgia Tech, we are able to do so in a data-driven manner. We are confident this change will balance the police workload in all zones. To illustrate the complexity of the problem, we start by explaining the Atlanta Police Operation System. Atlanta Police System is divided into 81 local police service area, which is usually called BITs. This is the first unit of the police resource allocation. Typically, for each BIT and each shift, there is only one response unit, which is normally a police car with 1 or 2 officers. Typically, for each BIT and each shift, if there's a no-one call in the BIT received by the call center, then the assignment will directly go to the officer of that BIT who has the highest priority to answer the call. The second level of the allocation is grouping the bits into 6 zones. The officers in the same zone can work together, and the cross-zone reinforcement are usually disallowed. This is pretty nice because a number of the police officers in the same zone can help each other when any one of them is busy. So now the problem can be simplified as how are we going to reallocate this bit into different zones? It turns out the only way is to share a large area to make the police workload more balanced. However, we don't want the zone to be too large, like the entire city. This will dramatically increase the travel time, which is bad for both response time and the police workload. So clearly, these 2 key metrics, response time and the workload, heavily dependent on the bit allocation. Now let's step back for a second and find out what is going on behind each 911 calls for service. First of all, we need to understand the process of a local police operation and how it relates to the police workload and the response time. Take BIT 202 as an example. Normally, there's only 1 police unit patrol in BIT 202, and this unit has the highest priority responding to the calls received in this BIT. When the 911 call comes in at the call time, a new incident record will be created at dispatch center and the call location will be recorded. If the unit of that BIT is available, it will set off immediately as soon as she or he receives the assignment and starts the investigation when the unit arrives at the scene. Once the police complete the investigation and clear the incident, the police report will be closed and record the clear time. If the unit of the BIT 202 is dealing with another call and not available at that moment, then the operator will find the nearest available officers in the same zone and assign the unit to handle the call. Similarly, this unit will travel to the location where the call received, then arrive at the scene, starts the investigation, and finally close the case. So here the time interval that the victim or the witness needs to wait for the service is called the response time. And the time interval that it takes police to deal with the call between the dispatch time and the clear time is called police workload. So to model such complicated process of police operation, there are 3 major challenges. First, the design has to be based on the predicted future workload, and it requires a statistical model that combines multiple sources of data in a systematic way. Second, the police operation for each zone is an independent, spatially distributed queuing system but inter-zone dynamics are determined by how we design the zone plan. Last but not least, the optimization problem itself has a bunch of realistic constraints that we have to consider. And solving this problem is computationally expensive due to the existence of our operation model. Now let's dive into the methodological part of this project and to see how we address these challenges. In this project, we redesigned the police patrol zones in Atlanta using a data-driven optimization approach. The outline of our approach has been summarized in this diagram. Our objective is to rebalance police workload in each zone by reallocating the existing police beats. First, we take advantage of the data from multiple sources, including GIS, demographic census, and most importantly, a complete set of known cost per service data collected from police reports. We then develop the statistical and operational models that are able to predict the police workload accurately given an arbitrary districting plan. Lastly, the final design can be found by solving a mixed linear integer programming based on the computationally efficient method. To be specific, the data sources that have been utilized in this study consist of three parts. First, known cost per service, particularly the data in Atlanta for the past 6 years. It usually contains the location of the call, the key timestamps, such as call time, dispatch time, which can be later used to estimate the police workload. Second one is the demographic census data collected from the US Census Bureau. Here we select around 20 census factors correlating the city's socioeconomic profile with the workload, such as education level, household income, median house price, and so on, which contain essential information about the development and economic growth of the city. These factors are particularly useful for us in making the prediction for the future demands. Thirdly, we also investigate the police travel time for each call, which will be used for constructing our operational model as well. In addition, we also use the geographical data, or GIS, provided by the government of Atlanta, which defines the boundary of the city and the corresponding current 6 zones and 81 bits. After discussion with police officers from the APD, we learned that what concerns the police most is the workload imbalance for a medium-sized or large city like Atlanta, which usually result in police overworking in certain regions such as Buckhead. So we follow the zone workload definition introduced by Michelle in 1972 and choose the objective function as the police workload amount, police workload variance among different zones, which quantitatively measures the police workload imbalance across the city. This metric was also used internally by APD to measure previous zone redistricting plan. So here, the capital D represent the arbitrary zone plan, and WKL represent the corresponding workload of zone K in year L. We also have to ensure that the resulting optimal plan is contiguous and compact. One of the major questions is, how are we supposed to determine the police workload WKL for each zone when we shifted plan V? The answer is certainly not simply summing up the workload of all bits in the same zone. Like we mentioned earlier, the dynamics of the police operation closely connects to the zone plan, and therefore the change of the bit allocation will affect both travel time and the waiting time. So that's basically why we need an operation model to simulate the process and calculate the workload accordingly given the different zone plan. Here, for example, assume we have 2 zones with 4 bits. Each car represents a bit and the color indicates which zone it belongs to. Now we have 2 different zone plans, D1 and D2, that we want to measure. In our framework, the proposed operation model takes the design as its input and generates the zone-wise workload accordingly. The operation model is developed based on multiple spatially distributed queuing system by taking advantage of the historical records of the police operation. Specifically, we adopted the hypercube queue model proposed by Richard Larson to model the police operation in a single zone. As you can imagine, for Atlanta, there's going to be 6 such queues interacting with each other by shifting the zone plan. For example, the figure illustrates a police system in the zone with 3 bits, where the states represent the status of the police officer's availability, and the green states or the long tail on the right-hand side indicate that all the police officers are unavailable. By calculating the steady state probability for each bit, we can estimate how many calls will be assigned to each one of the units and its corresponding travel time. Therefore, the zone workload can be obtained by summing up the unit-wise workload in the same zone. Here, we use the real data to evaluate the effectiveness of our operation model. The blue bars are the simulated output for a particular year or zone, and the red bars are the ground truth provided by the real data. The result shows that our model can capture the dynamics between zone plan and zone workload pretty well. However, I want to emphasize that it is impractical to carry out such computation for the purpose of zone redistricting, since the decision space is extremely large. For example, with 6 zones and 81 bits in Atlanta, this will generate more than 2.4 times 10 to 59 possible zone designs. One simulation given the design takes up to half an hour to carry out the computation. So here, we use a linear function to approximate the simulation results. On the right-hand side, the blue line is the simulated objective value on the different design, and the red line is the approximation. As you can observe, that our linear surrogate can achieve a nice performance of approximation. Using this method, we can dramatically simplify the evaluation of the objective function. In the end, we replace the police workload expression using our linear model and translate the contiguity and compactness into a set of linear constraints. Eventually, we turn the problem into a mixed linear integer programming, and an optimal plan can be found by performing a heuristic search given the current design as the warm start. In the third part, I'm going to describe the implementation of our zone design in Atlanta and its impact. In January 2019, after several rounds of discussion, we presented our final proposal plan to Atlanta Police Department. This plan was chosen among several candidates because it greatly reduced the workload imbalance while requiring minimal bit reallocations. As you can see from these 2 maps, the colors which indicate the workload in each zone are more evenly distributed under the new design on the right compared to the old design on the left. We achieved this reduction by requiring only 4-bit changes, as fewer changes will simplify the implementation process. The area involves in the proposed changes are here, for example, the bit 103 has been moved from zone 1 to zone 5, 203 moved from zone 2 to zone 1, and 213 is moved from zone 2 to zone 6, and the bit 506 is moved from zone 5 to zone 6. Also, new plan, zone 6 in East Atlanta increases by 4 square miles, and zone 1 in Northwest Atlanta increases by 2 square miles, and zone 2 in North Atlanta decreases by 7 square miles. We also made simulation studies on the changes in workload under the new design using historical non-call data and forecasted demographic changes. We predicted that the new design will decrease the citywide police workload variance by 62.8% in 2018 and by 55.9% in 2019. And this is the timeline for our implementation. After almost a full year after the project started in 2018, we finalized our proposed zone design with APD in January 2019. A few weeks later, the APD presented this plan to Atlanta City Council for consideration. During the process, we were in close contact with the APD and to help them analyze the details of the expected changes and address the questions raised by the city council members. The city council voted to adopt the new design in February 2019, and the new design was officially implemented in March 2019. And after implementation, we spent one more year collecting data in order to evaluate the real world impact of the new design. In the second half of 2020, we received a new batch of 911 call data from APD. This allowed us to evaluate the real world impact of the police zone change. We compared the 2 years of data before the implementation and the 1 year of the data after the implementation. Here we specifically choose March 2020 as the cutoff time in analysis because this was when the COVID-19 pandemic caused the citywide lockdown in Atlanta, which significantly changed people's behavior and the police operations. So we exclude the data after March 2020. Our analysis shows that the citywide workload imbalance has reduced by 43.5% in the year after the new design was implemented. You can also visually see this effect from these figures as the colors on the right are more evenly distributed compared to the ones on the left. If we focus on the zone 2 in North Atlanta, which had the highest workload among all the zones before change, we find that the total workload in this zone has reduced by 7.25% in the year after the change, and the crime rate has also dropped. In addition to police workload, we also look at other metrics that are directly linked to the public perception of police official efficiency. These metrics include the response time, waiting time, travel time associated with the high priority calls such as burglary or other serious crimes. To remind you the definition, waiting time is the time between a 911 call and the police dispatch for that call. The travel time is the time it takes for the dispatch unit to arrive at the location of the call. And the response time is the sum of the waiting time and the travel time, which measures the total time from a call being initiated to the police's arrival on the scene. And this table shows our analysis result. We find that the average response time decreased by 5.8% year-on-year ratio compared to 10.9% increase in the prior year. The waiting time had a big increase by 36% in 2018, but it decreased slightly after the new design was implemented. Finally, the travel time had a big drop onto the new design, as the average travel time decreases by 24.7% from 10.7 minutes to 8 minutes. Therefore, all 3 times metrics improved after the zone change. Our project also received prominent news coverage from multiple news outlets. This includes an official news announcement by the APD on their website and the coverages by the Georgia Tech News. We also received coverage from newspapers and TV, including the Atlanta Journal-Constitution, the largest daily newspaper in the Metro Atlanta, Fox 5 News and Channel 11 News. The police zone change also generated discussion on social media for local communities such as Nextdoor and The Patch. The newsletter of the Buckhead neighborhood also reported that as of October 2019, the area saw a 17.7% crime drop comparing to the same period in 2018. After the zone design project with the APD, we have been contacted by police departments in other US cities to make police zone redesign in their district. We have successfully collaborated with the city of South Fulton, a newly incorporated city bordered with the Atlanta in the south, and implemented a new police zone design with SFPD in February 2020. We also are in discussion with police department from Spokane, Washington State, Stanislaus County in California, Fulton County in Georgia to initiate similar projects. Finally, we have made our mathematical models and the source code for police zone design publicly available on GitHub. So they are freely accessible to any researcher or police departments who wanted to try our data-driven police zone method. So in the end, to summarize this project, we propose a data-driven optimization framework for police zone redesign with an implementation in Atlanta. The Georgia team consists of Professor Yao Shi, PhD student, Woody, myself, and we also had several undergrad and MS students to help us collect and process and analyze data, include Alex, ALOC, and so of course, this project would be impossible without the support from Atlanta Police Department. We especially want to thank Major Quickly, Green, Major John Quickly, former APD and Chief Eric Shields for their tremendous help throughout the project. And finally, we're grateful to the Atlanta Police Foundation and the National Science Foundation for supporting our work. So that's the end of our presentation. Thank you for your attention.